Good afternoon, everybody. My name is Mehdi Salimi from Carleton Polytechnic University and British Columbia, Canada. I'm going to talk about uh, our paper, which is a joint paper with Alireza and Tahere, which is titled Two Norm Groups: Unraveling Computational Properties of Two Norms. In this presentation, we investigate on two norm groups, and this study begins with the introduction of two norm on groups and the provision of the illustrative examples, including the discrete Heisenberg groups, to demonstrate the utility of two norm on groups for computational applications. And then we establish a series of theorems to explore the relationship between this framework. And then we offer some finding concerning homomorphisms on such groups and the two norms of the discrete product of groups. The first attempt to introducing K-norm was introduced by Woodlich in 1933. Then he investigated two metrics and two norms in 1963. Gahler, with his colleagues, continued this work, and then they introduced N metric and N norms in 1969. And then many mathematicians paid attention to the theory of two norm spaces and significant results, including fixed point theory, approximation theory, and so on. Let's start with the definition of two norm spaces. Assume V is a vector space over the field R with dimension at least 2, and we have this property, this which is called two norm, is a function from production of V by itself to all non-negative numbers with 0. And let's have these four properties. This norm for all elements U and V in this vector space are non-negative, and if we have this condition, then U and V are linearly dependent. This notation is commutative. It means norm of U and V equals norm of V and U. And we have property number 3, which is called scalar multiplication, and also property number 4, which is called triangle inequality. If this notation, this function, has all these four properties, then this notation is called a two norm over V, and this pair is called two norm spaces. Now let's switch to norm groups. Norm groups, which are in fact groups with a right invariant metric. In 1936, Birkhoff with their colleagues independently proved a significant theorem. A Hausdorff group K is homomorphic with a metric space if and only if K satisfies the first countability axiom. It means each actually neighborhood has a countable basis. They also showed that this group has a right invariant metric. The theorem then became known as Birkhoff-Kakutani metrization theorem for groups. And then in 1950, Klee studied invariant metric of groups to solve a problem of Banach. Groups with invariant metric recently have played a role in the theory of topological groups. Let's continue with introducing definition of norm groups. Let L be a group with identity element E. A function, actually norm, from this L to all real numbers is called a group norm if we have all these following properties: symmetry property, triangle inequality, and positivity, and also this condition. Then L equipped with a group norm is said to be norm group. uh, we have one definition which is about dependent and independent subsets. Let L be a group and this set of elements be a subset of L, then this set is a dependent subset of L if there exists some elements at Z such that at least one of them is not 0. And we have this condition, otherwise we say all these elements are dependent. And definition of two-norm group, let L be a non-trivial group with identity element E. A function from L times L to all real numbers is called a group two-norm if the following properties hold. We have non-negativity condition, we have commutative condition, and this like inverse condition, and also triangular condition. Then this pair is called a two-norm group. There are some results, let me skip it, and one proposition that says if L is a two-norm group and then we have all these conditions, then M equals minimum of this set. We have this condition. I know this work is a little abstract, but all of them have application in the proof of all following theorems. One example, let L be this 3 by 3 matrix with all elements in Z, and this denotes the discrete Heisenberg group. And let's put Heisenberg, the norm of V of S, Heisenberg norm of V of S equals absolute value of this difference, where V is defined by this matrix and S defined by this matrix. A prime is just an element which is different with A. It doesn't have any special meaning. And then this Heisenberg norm is a two-norm on L. It has all properties that I showed you before. And this is the Python code to compute two norms of Heisenberg groups. This Python code was done by Alireza. And another example, let R star plus denotes the group of positive real numbers with multiplication as the group operation, and L is this. By setting this norm equals this absolute value, okay, where V is this pair and S is this pair. Again, A prime and B prime don't have any special meaning. It means just they are different with A and B. Then this L will be a two-norm group. Let Z by Z is defined by all ordered pair AB such that A and B are in Z. Then with a binary operation like this, and by setting this two norm, it's just a random definition of two norm, then this L is a two norm group. We just wanted to bring some examples about Heisenberg groups or Heisenberg norm and also two norm groups. There are some results that they show interconnection between two norm groups. For example, this definition, which is a definition of convergence sequence, and also after this, with using that definition, we can define two Banach group, similar to Banach group, but here we have two Banach group. And also some lemmas. For example, this lemma says that if this pair is a two-norm group and we have this condition for all S in L, then V must be identity element. Another lemma for a convergence sequence Vn in a two-norm group, if we have this limit, then we can move limit inside of the norm. All the proof of these theorems are available in the paper that I submitted to this conference. And the main theorem of our work, let L and true norm be a true norm group, then the true norm is a continuous map. Again, the proof is actually beyond the patience of this conference. That's why I left it. If you want, you can find it in the publication of this conference. And next proposition, in a two-norm group L and this notation, it was two norm groups that I explained before, the following statements are equivalent. If you have this condition is like triangle condition, a little similar with that. This equivalent with 2. We can go from 1 to 2 or 2 to 1. And also another lemma, direct product of two norm groups. If we have this two norm and this two norm, then this is a two norm group with respect to two norm defined by this and this respectively. And the last theorem, the paper has 3 main theorems. This is the last one. Let L be a finitely generated abelian group with this condition, then there exists a pseudo two norm on L. And conclusion, and don't repeat it again, and list of references. I know this work was a little abstract, far from tangible application, but pure mathematics have application in applied mathematics. Thank you for your attention.